sure.
Let's see. Okay, great, works.
Oh.
No?
Ah,
yes, it is. Okay, fantastic. Thanks a lot for the help. So let's continue. We just introduced a little bit the background of the simple picture of how the London level looks like in graphene and how the quantum Hall effect is supposed to be in graphene. And then we went through the twisting system of the first one experimentally discovered in graphene and HBN. And then we know that now the whole technique can be applied to many kind of two-dimensional materials, including TMDs, including whatever you name it. So then we continue to the next section, which I call it as a lattice moire and Stucky potential and beyond. And you know, the moire system was mostly realized by twisting the lattice of two-dimensional materials. So there's another system people have been working really hard. Theoretically, that is a two-layer of graphene, semi-metal, direct fermions. There's no strong interactions, whatever kind of E interaction. There's no superconductivity, nothing, no magnetism, from two sheets of just a single particle picture. You just put them together and align them. If you align them correctly, when I say correctly, it means you have some numbers, some magic angles. It happens that if you put them close to or at the magic angle, the direct peak will be gapped out and central band will become a flat band, and bandwidth is only about a tenth of milli-electron volt. And that's great because it's almost a gift from nature. Why we say that? Because people can easily obtain that in almost very low cost. You just scratch your graphene on the wafer. You just collect two pieces, you stack them, try to control the angle a little bit. Of course, there was some tricky and some sample yield you have to pay attention to. At the end of the day, you will get the sample, you cool it down, you will have a flat band. And this flat band is at the Fermi surface. You can tune the Fermi energy because the Moire unit cell is in a very favorable, say, experimentally favorable size that when you have two graphene shifted, for example, at 1.1 degree, I will go to that slide later, at this angle of twist, you have a unit cell of Moire length of only 12.8 nanometer, and that's correspondingly to, for example, if you have a full filling of this Moire unit cell of 4 degeneracy, 4 electrons, that carrier density is only 2.8 times 10 to the 12th centimeter per centimeter square. That means using this conventional CMOS technique through any kind of dielectric, you can easily obtain that. And the limit we showed you yesterday, the maximum carrier density we can obtain through this gated dielectric is about 1 to 10 to the power 13th, right? So it's just a portion of the maximum we can afford. And so with this, people can really study. It's not too large, it's not too small. Before you break down your dielectric, you already saw this phenomenon, and you have good enough resolution to really see the phenomenon. And that's a very, very, say, miracle system. And that's some basic numbers for that. Okay, so why 1.1 degree is so much important? Let's look at this twisting again. Before, in the previous session, I showed you twisted model between graphene and HBN, which has a lattice constant mismatch of 1.8%. And now if we have two sheets of graphene, imagine we forget about relaxation or kind of deformation. The ideal case, you have two lattice mismatch equal to 0 case, and there is a Moire also showing up in the system. If you twist them and you diminish the angle from large angle to small angle, at some point this band is squeezed and flattened out. And at 1.1, there is a tiny gap between the dispersive band and the flat band. So it's gapped. And it can be possibly because in this scenario, the symmetry is now different. You can create a symmetry breaking by C2Z symmetry breaking. You can create also turn bands, which is topologically non-trivial in the system. But at least with this one, we can see that 1.1 is the first angle when you approach from large twisting to small twisting angle. And this is not the only one, because by this, by calculating from the very first paper in 2011, I didn't put McDonald's photo here, So on the left-hand side is McDonald's work. So he found that if you make some kind of effective band velocity, there is a bunch of minimums. That means except for 1.1 degree, you should have 0 point something, 0.0 something, a series of minimum that the bands are flat enough. And this picture, if you use this purely numerical calculation, it's a little bit hard to understand. And there is an easy way to understand that phenomenon, which is invented by these two guys. You just rewrite this Hamiltonian into some form, you will get this vector potential out of that. So there is an effective magnetic field, which is using this formula. We got the effective magnetic field defined by this little one, and we can then imagine that this effective magnetic field is making the particles into a rounding orbital, and there is an effective LB also, which is magnetic length and defined area. Okay, this area we call it S naught. And there is another real area in our system, which is in real space. You have a Waals wavelength square, which is approximately the lattice constant A square over the twisting angle theta square. And these two areas, when they match, when there is an integer filling of omega AA, the real Waals unit cell size, the area, there is an integer number times S naught equal to that. Each time you match this sequence, you will have a magic angle. So that's called a pseudo number level picture to understand this magic angles. And in graphene, the first row of data is taken from this Peanuts paper from McDonald, and the second row of the numbers very closely to the first row is just by comparing these numbers when the two areas size matches each other. So apparently it's a very good, easy way to understand that actually this various curvature and effective magnetic field is playing a role of flat band in somehow in the system. So, but if you do the experiment, you will easily find that the sample yield is extremely low. Why so? Before we go into more details, we can have a look into the literature. People manage to study the system in real space in many kind of methods. For example, people do the near field optical measurement. You can see this. There was some distortion of this Markov pattern, and also people did. I think this is some either STM or PFM. I don't remember. You can see that although locally, if you look at one triangle, well defined, it's quite okay. But with a large scale, we have boundaries and twistings. But these kind of inhomogeneities is killing the global effect. If you make the samples, you have only like 1/20 devices working if you want to have this flat band. That's why it's very difficult. And why it was not discovered before, because the first experiment showed up very late, like in 2018, I don't remember. So because at the beginning there were people who tried hard to do this graphene techniques. For example, people that cut this graphene by laser using the heat, and the atoms are just evaporated. You got a single crystal graphene sheet into several sections. You can stack them, and this was studied in 2016 with the advanced material paper. But unfortunately, they didn't really decrease the twisting angle. They have a very good starting point. They have 2 or 3 single crystals with exactly the same orientation, right? Because they are coming from one single sheet of graphene. So with this exact same orientation, which is important to control the twisting angle in the next steps, but they missed it, and they didn't even do this transport measurement. They were carrying out some kind of just the exhibition of different stats. That's it. And there are also some kind of measurement here showing that locally you should have some kind of Waals lattices. And then in 2016, there's also a PIL paper from the same group later on from Pablo's group. What they found is that they tried hard to align, because there were predictions from McDonald that 1.1 should be the magic angle, you should see a flat band. They tried hard to align the samples, but they didn't start from a single sheet of a single crystal. They tried to find the graphene with straight angles, and when you pick up one flake, and the second one, you add twice the error to twist this angle. So at the end, they saw something very close to. They saw some flat band and some interaction-induced insulated band, but there was no the famous superconductivity showing up because the angle is not small enough. So later on, there is also some improvement of this system. They also found this insulating band can show up at different angles, but somehow none of them was able to achieve exactly 1.1 degree because the tolerance of obtaining the very flat band of graphene at 1.1 is only around 0.1 degree. So if you have a 1.3, you miss it. You will have only some kind of insulating behavior. You don't have the opportunity to see superconductivities and other things. Until they found a way very similar to the one I just showed you from this laser cutting. They found a way to cut a single crystal graphene sheet by AFM tip. So you just cut a very fine line there, and you will have two flakes of graphene, which are supposedly from a single crystal. They should be exactly the same orientation, so that when you pick up the first one, you have only one chance to have errors of your twisting, and then you just put the first one back to the second flake. So the error of misalignment is much better controlled in this manner, and then people really managed to find the first sample showing the evidence of like a mod insulator and accompanied by two superconducting pockets. So this is the big deal in condensed matter physics. So they published two papers in a row, and one is showing superconductivity, the other is showing like interaction-like behavior of mod insulator, and it was happening, I think it's 2018. So till now, the twisting system of two-dimensional materials is almost complete. So people found that graphene on BN is giving these Waals-induced side peaks, and the two graphene flakes can induce a very fancy physics that happens at the magic angle at 1.1 and even smaller angle for example 0.53. You should have flat bands. You should have interaction-induced phenomenon because the band is flat enough, the effective mass is large enough so that the momentum, the kinetic energy is much suppressed, so that the comparison between the Coulomb energy and the kinetic energy are different. And when the Coulomb interaction energy is dominating, you'll have a lot of interaction physics. So that's then after this, the whole field evolves very rapidly, and people found that if you have some alignment between, for example, the one of the surface of your twist graphene system and the bottom edge BN, because everyone is encapsulating BN with graphene, and this is the first evidence showing that when you have an alignment of one of the surface, you should have some orbital ferromagnetism showing up. And we know that each layer of graphene has nothing to do with superconductivity. None of them is magnetic. But when you have a twist, flat band, and then you have a misalignment or alignment between the bottom or top surface of HBN, you will induce a lot of new physics. And the previous one is just, like Van Hoff singularity behavior. When the density of state is too large, you have superconductivity. I wouldn't say people have fully understood the physics of superconductivity in graphene twist system, but at least this magnetism and the churn bands are quite well understood up to date now. So there are some papers coming out in the very similar age from Spain, from the US, from Europe and China and other groups, all reporting very fancy physics of this flat band. When you have partial fillings, you have insulator which is accompanied by superconducting pockets. Whenever you have a sample with this 1.1 degree aligned of twist by the graphene, you have similar results. Depending on the sample quality, people get different pictures, and people try to understand by playing, for example, applying the hydrostatic pressure to the system, and the superconducting transition temperature changes a little bit. People try to place a SOC material, for example, some kind of TMD underneath the system. Superconductivity interaction also changes. So there are a lot of parameters people can tune. Actually, this toy model is great for condensed matter physics. And there were some big events. I just named a few of them in the history of twisted graphene. From the first one, people saw some kind of this interaction-induced insulator, and then 2018, the first evidence of superconductivity. In 2019, the first evidence of some kind of magnetism. And then in 2020, Andrea Young's group found that if you carefully make the sample quality better, well aligned, all these anomalous Hall can be quantized. And they can be quantized at zero magnitude field, which is a quantum anomalous Hall effect. And quantum anomalous Hall effect is a dream, it's a holy grail in condensed matter physics. And, people have been doing that since the day of topological insulator. They try to dope the topological insulator with, for example, magnetic dopants, and to achieve the same experiments. But that one in 2013, if I remember correctly, was at very low temperature, like millikelvin. So the topology is very fragile. And here it's already 1 point some Kelvin. Even at 4K, you have well quantized plateaus. So that's helium temperature already. So it's a great achievement that in graphene, just by twisting, by alignment, you will have a topological non-trivial band showing up, which gives us the dreamed quantized plateaus at zero magnetic field, but still at very low temperature. And this year, in 2024, there were even more interesting papers coming out by using the material system of, for example, twisted MOT2 or ABC stack graphene, 5-layer graphene. They can see fractionally quantized German insulators at zero magnetic field. So the plateau is not even integer, and now they can be a fraction, for example, 2/5, 3/7, and 4/9, and etc. So they're just mimicking exactly the same physics that people were studying in the 1980s, 1990s, 40, 30 years ago at very high magnetic field, but now everything is happening at zero magnetic field, of course at very low temperature. And this is a very important branch of condensed matter physics in twist angle graphene. Of course, later on, people should be look for example, even denominator and couple the system to superconductors, and experiments will become more difficult, but the physics is clear there. And this is the one I just mentioned. So in 2023, the two papers come out in the same time, almost, the two groups. One is from Shanghai Jiao Tong University, the other is from Washington University. They studied the same system with a tiny difference of the contact method. But at the end, they report the same result, that if you twist this MOT2 by an angle of 3 point some degree, you will have an integer and a fractional quantized plateaus at zero magnetic fields, and the phenomenon is very beautiful. So that's how it was evolving in this system. So in the rest of this today's course, I would introduce you something different. We have went through all the history of the first conventional quantum Hall and twisted Moiré, and then magic angle graphene, and then all these topologically non-trivial Chern bands in twisted graphene. But all of these experiments, for example, are given in a certain material. If you have a graphene, the lattice confidence is fixed, is 0.24 something, you cannot change it, right? So all these, let's say, is in the manner of you just try to hit and then discover whatever you get. And there should be a number of unexplored area that, for example, if we have artificial superlattices, then the whole physics can be somewhat different, because in the graphene system the angle is fixed, the match angle is fixed. It's just there, and people can go in the same fixed phases to do the physics. So the challenge is there. How can we explore some new uncharted territories in the Moiré superlattice? And the answer is maybe we can find some superlattice. Instead of the lattice mismatch created in Moiré, maybe we can have some interaction from electrons, because in condensed matter physics we know that when electrons the interaction is strong enough, they can form crystals. For example, the CDW and Wigner crystals. It's very simple. You should have the ground states with different symmetries, different lattice constants, and that's the concept of the next section I'm going to introduce you. So if you have, for example, in the first hand, a electron interaction-induced superlattice, then you use that one as a superpotential, a Coulomb potential, because by definition, the electron crystal is an insulator, and it creates only a superpotential, not participating in the transport. So if you put another layer of two-dimensional electron gas, for example, graphene, on top of that, so there should be some interaction between them. And the difference is that now the lattice of electron interaction defined superlattice is no longer bound by the lattice of the crystal themselves. It can be free electron formed from interactions. We call that Wigner crystal later on. And also, there could be synergetic interplay between the two systems. For example, the existence of graphene may enhance the critical temperature of that, and that one may enhance this Coulomb interaction in graphene. That's our concept. And at the very beginning, we did experiment in some kind of insulator system, but later on we found that in literatures, like 2 or 3 years later, there are indeed a lot of experiments coming out already. For example, we know in Margay superlattice of tungsten diselenide and tungsten sulfide, this system creates automatically a Wigner crystal, which is a real Wigner crystal. People found that by STM evidences, there are partial fillings when n equal to 1, equal to 2/3, and 1/3. There's indeed a possible way to create Wigner crystals, which is defined by Coulomb interaction in such system. And using this kind of system, you can do the coupling of another layer of filial graphene and this superpotential from the Wigner crystal. And indeed, you can see that the thing can show there you have lines of partial filling. That means you have a Moiré unit cell, but this Moiré unit cell is not from lattice. It's purely from electronic interaction, and the size can be well defined, which is in very good agreement from transport evidence and the STM evidences. So this is one of the examples how this kind of electronic superlattice, interaction-driven superlattice, can act as a superpotential instead of the real lattice ones for our 2D electronic heterostructures. So then we will go using our technique here. Before we do all these details, we would like to remind you again. So we know that when we plot every two-dimensional electron gases, including the topologically non-trivial systems, in the coordinate of temperature and the magnetic fields, so far everything is squeezed in this lower hand and right part. You know, there were some FCIs, fractional churn insulators. There were quantum anomalous Hall effect. They need no external magnetic field, but they have to be placed in a very low temperature. And for application, we need at least nitrogen temperature, let's say. Nitrogen is easy and cheap to get, and better we should expect something happening at room temperature. That will be ideal case. But in other systems, for example, the tellurine and doped graphene, although they can have very high temperature to have these quantized plateaus, they need a very high magnetic field as well. So it's all of them are so far not there yet, at least at this point, for real application. And we just introduced you in the previous, the first half of today's section, that the Lambda levels of a monolayer graphene is defined purely by this formula. So it's proportional to Fermi velocity. And in this square root, everything you cannot change, because the maximum magnetic field you can obtain on Earth is 45 Tesla, and everything is constant. So the only thing you can change to increase, for example, the Lambda level gaps in graphene is to increase the Fermi velocity. That means to make graphene run even faster, because we already know that graphene is a relativistic direct fermion. The Fermi velocity is already 1/300 of the speed of the light. It's high enough. How can it be even higher? And there is indeed possibilities, which is to enhance the interaction between graphene. So it's not a new phenomenon. It has been studied. You know, yesterday we mentioned to you that if you suspended graphene, except for this very clean quality you got, very high mobility you got, you can also enhance the interaction at the vicinity of direct cone at the direct point. And as a result, the Fermi velocity can be renormalized by a factor of 2 or 3, and that means the cone is even sharper. There is a logarithmic interaction in the system, and it's been studied both theoretically and experimentally in 2011. So that's a very early result showing that by just suspending graphene, by diminishing this denominator of dielectric constant of the environment, you can enhance the interaction between graphene electrons, and you can make the velocity higher in the system. And this is the hint from literature. So our way to achieve higher velocity, and at the end, this larger lambda level spacing, at the end, the easier way to obtain quantum Hall effect is to find an electronic crystal system. For example, we know that the Wignall crystal is a well-known phenomenon that if you have an electron gas with all these parameters defined, you will have a RS. The RS is a criteria to judge if your electrons can have the ground state of electronic crystal or not. For example, for three-dimensional case, this value has to be larger than 106. And for two-dimensional electron gas, or quasi-2D, you need a RS over 31. That means as long as you have a system with an effective mass and G factor, everything, full radius, you run the numbers. If RS is larger than 31, at the end of the day, at the ground state, you will have an electronic interaction-induced lattice, which is called electron crystal. It's purely electron interaction. It has nothing to do directly with the lattice of the host material, but a new order that is created inside of the material. Okay, so this is some of the evidence I already discussed with you, and our experimental setup is very easy. We chose a material which is called chromium oxychloride, and this thing has a anti-ferromagnetic ground state at a Néel temperature of 13 Kelvin, and this magnetic ground state didn't really participate too much in the transport. I'll show you later. The whole thing we just changed is that instead of encapsulating graphene in 2 layers of HBN, we just replaced the bottom one by chromium oxychloride. And the device is the standard one with the 2 gates equipped so that it can have a vertical electrical field and carrier density tuning at the same time, as we discussed yesterday. So this is a whole bar structure at the end of the sample. The scale bar is about, I think, either 5 micrometer or 10 micrometer, don't remember too much. Then we got the result of the dual gate mapping again. We saw that for bilayer graphene, for example, or monolayer graphene, for example, yesterday, that the direct peak, which is the minimum of density of states, should be diagonal for the conventional case. But in the case of our setup, you just replace one of the bottom substrate by, chromium oxychloride. The whole thing is changed. There is a more resistive peak showing up, and it's bending back. So we mark all these spaces into hole, and electron. That means this is the new charge neutrality point defined. And we know that is because we measured this Hall effect under a finite magnetic field. So this is a controlled sample of conventional graphene. It should look like that. This is the charge neutrality point, and where the carrier density is supposed to be 0. Okay, and this is the sample of chromium oxychloride replaced ones. And if we plot them from the dual gate mapping, which the color represents the resistance of the device. If we plot them from the dual gates into displacement fields and total carrier density using the formula we discussed a little bit yesterday, but not very precisely. Now this is a precise formula. You can see that there is still the vertical one, but stops there and then goes to another direction. The whole y dashed line, the new charge neutrality point, and everywhere else is separated into the conduction band and valence band, which is corresponding to electron beam holes. Why so? So the reason is that there's some kind of surface state. I will discuss that later. But let's first put the sample under a magnetic field and see how the number levels look like, and then we'll have a clearer idea of the field fractions and the phase boundaries, for example. So this is how it looks like. It's the same map of this one. This is, instead of with a field, there is no magnetic field. And this one is under a magnetic field of 14 Tesla at 3 Kelvin temperature. So you can see that there are clearly several distinct phases from each other to another phase. For example, on the left hand, if we make a line cut of this red dashed line, and if you run the measurement from 0 magnetic field to 14 Tesla, and you make a map using the spacing field as a parameter and the magnetic field, you will see the conventional like graphene lambda levels or SDH oscillations, which starts at a few Tesla and then oscillates into quantum Hall plateaus. This is very conventional and as usual, okay? But if you do the same mapping of electrical field and magnetic field using this IXY as a representation, you can see that along this green dashed line, the whole thing is changed. So instead of this conventional picture, now the graphene is behaving very strangely. So which is mind-boggling because the blue color and red color here represents two Finner fraction of +2 and -2, which is the quantized plateau. All the areas is not a cutoff of plot. It's purely measured data. They are like it's 12 something kilo ohms, and then it extends to very low magnetic field, almost hitting the B equal to 0 line. So it's almost impossible in graphene before even the best quality of graphene has to have the quantization at a portion of some Tesla. Here it's almost 0, and this is a line cut of 12 Tesla behavior. You see the plateau is well developed. If you plot everything back again in the three-dimensional picture, it will look like this. So if you are the first time looking into the data, it might be a little bit strange, but if you just look carefully and divide them into different phases, you will really understand that, along these new phases showing up on the right hand, you will have a crossover from fan-like Landau fan into a cascade-like Landau levels, and this little thing is plotted in the real space, in the real coordinate of B, N, and D. Now you have an idea of how low the magnetic field is required to have a quantized plateau in the new system as compared to the same device, same measurement, but from at different gate voltages. So you have two phases largely distinct from each other. If we look at a line cut of this mapping again, which is the one I showed you on the right hand, if you look at that again, you make a line cut close to delta D equal to 0, which is this line, you will have a quantized plateau showing up, which mimics very likely a quantum anomalous Hall behavior. Instead, that quantum anomalous Hall has a residual quantization, even the B is equal to 0. Now we need some finite magnetic field to see this phenomenon. This is basically how it looks like at a very low temperature. If you change the temperature from 1.5 Kelvin to 120 Kelvin, the whole behavior is preserved at very high temperature. So that means the anti-ferromagnetic ground state, which has a melt temperature of 13 Kelvin, somewhere here, is not a factor which determines the observation. So something is not related to the magnetism of the substrate here. It prevails to a very high temperature, and this is what we were discussing before, that at 80 Kelvin, which is right above the liquid nitrogen temperature, we'll have a quantized plateau at 0.3 Tesla. So 0.3 Tesla means if you go to the Amazon, you buy a magnet, the surface magnetization strength sometimes can be larger than this value, 0.3 Tesla. Then if you have one of the sample, no twisting, easy encapsulating from HBM and chromium oxide and a layer of graphene, you put the device, you put the magnet on top of that, you throw the system into nitrogen, you will get a quantized plateau. So that's the most relaxed experimental condition ever discovered in any kind of two-dimensional system. It's a world record so far. So that means somehow by just changing the substrate of HBM into some kind of new material, we got a larger Fermi velocity and larger lambda level spacing and more robust quantum Hall effect. So this is the experimental data as compared to all the existing system that is still graphene but just modified. Okay, and this is one of the way to have sacrifice a little bit of magnetic field, but significantly enhance the temperature to observe this experimental phenomenon. Then we have to understand that what's happening, what's going on in the system. So we started from a very conventional way to understand the system. First of all, we would like to extract what's going on there in the low field limit. For example, if we measure the Hall effect, we'll have carrier densities well defined at each point of this x-axis, which is n total. Then, if conventionally the n total should be following the white solid line because it's a capacitance coupling from the gate, right? It has to smoothly go from hole side to electron side without any interruptions. But this one, along this line cut at D effective equal to 0.35 volt per nanometer, everything is following at the beginning the white solid line, but then departs from some point and it starts at the negative value until everywhere. So that means all the electrons supposedly should be injected from the gate into the graphene, didn't go into the graphene. The graphene stays in a state of hole dot manner. And then there is a mismatch. For example, if you subtract this white line with this red line, you will get some missed electrons going to somewhere, right? And the value is about 10 to the 12th, 10 times 10 to the 12th, which is 1 times to the 10 to the 13th. It's a quite high carrier density. All this carrier density didn't go to graphene. They have to go to somewhere. That's our first hypothesis. The hypothesis then goes, when it goes into reality, it has to be, for example, a surface state, for example. And the surface state cannot be in vacuum, right? So we have to imagine it goes to somewhere in the surface of the material chromium oxychloride. We define a depth of D, that all the electrons supposedly should go into graphene, didn't go into graphene, but they went into all these surface states, and we assume them to be a quasi two-dimensional electron. That's another assumption. And then the whole system very simply changes from a two-capacitor model into a three-capacitor model. Then you just solve the Gauss equation. You will have a isopotential plot obtained from the right panel. So if you compare that one with the number levels we obtain, each number level is a fixed filling fraction. That means a fixed carrier density. And that is an iso doping level, okay? So these two looks very similar. And the one there's a well-defined phase boundary, there's a CMP, and the CMP is experimentally also thin. That means even without any interaction of Coulomb interaction, using the very simple model, or together with some assumptions, we will already reproduce the data, to some large extent. That means this hypothesis might be correct, okay? So there should be indeed a kind of surface state in the material down there of graphene. So then we can do some DFT approaches using the hypothesis from conventional classical model. So this is how we did. We have chosen an interfacial band, which is when you have the electrical field applied vertically, there is the lower end of the interfacial band, which is flat enough so that all the electrons, as long as you have electrons transferring from graphene into that surface band, they will form a kind of electronic crystal, and that's the picture. And indeed, if by computing this RS value I just mentioned before, there were a bunch of systems in this table, and if you are interested, you can look into more details in the theoretical paper of this paper. And there are a bunch of them should show the same behavior, and 2 of them are already experimentally proven. One is the chromium triiodine, and the other is our system, chromium oxychloride. So this is the other system published in 2022 in Navigator, so from Washington University. What they saw is another system. Instead of using HBN, they use a chromium tridiode, and then the graphene is showing very similar behavior as our system, but the data quality is somehow a bit lower, but you can see that the quantization happens at a lot lower magnetic fields compared to the conventional phase. That means the effect is universal. It can be repeated in different systems, and in our system, we managed to understand that. So the way the whole thing is happening like this, if you have an insulator beneath graphene, at the very beginning, the surface band of the insulator is not filled at all. So the graphene is a conventional graphene, and under magnetic field, this number levels is formed, you have a quantization as in conventional graphene. As long as the two Fermi level is matching, the charge transfer can happen from graphene to the surface states of the insulator. And then because naturally it forms, because RS is larger than 31 by DFT calculations, naturally they form a new set of superpotential underneath graphene. And this superpotential changes the band structure of graphene, makes the cone sharper, and then the Fermi velocity higher, so that you see a new phase that is much more robust in terms of quantum Hall. And this is also proven by STH oscillations experiment. For example, if you measure this conventional phase STH, the quantum oscillations are disappearing at a temperature somehow 40 Kelvin. But in the new phase, where supposedly we have this electronic crystal, the oscillations are preserved at 120 Kelvin. So everything is in agreement. That's how we understand the system. And this is a kind of possibly usable in the future. For example, if we enlarge the size of the device into like 50 micron by 50 micron, we can do the quantum matrix measurement. And this precision can be now about 10 to the minus 4 up to 60 Kelvin, which is a lot higher in terms of temperature, but the precision can be improved further. So that's the system we would like to introduce you for today. Okay, so it's great timing. That's almost hitting the end of the course. Thanks a lot. And let's discuss a bit more some other system in the next session. Thank you.